Hello and welcome back. Before we actually do more proofs, we've got to do a review of some logic terms, the contrapositive and the converse. So, to get a good idea how this works, I think we should gaze upon this picture, this Venn diagram thing. So, this is the way I visualize in my head what it means if I say if P then Q. It means like any situation where P is true automatically means you're going to be in Q. Then Q is going to be true as well. And that's equivalent to saying if not Q, then not P. Because if like you're out here somewhere, like not Q, being outside of Q also excludes you from P. So these two sentences are logically equivalent, these two statements here. And one is called the contrapositive of the other. And that's not the same thing as the converse. The converse is if you change the order of the P and Q. So you don't negate them, you just say if Q, then P. And this is what the Venn diagram looks like in that case. So if it is true that if Q, then P, that means whenever you're in this Q thing, you're also in P. So if Q is true, then P is true. That's equivalent to its own contrapositive, where if you change the order of the P and Q and also negate them, you get if not P, then not Q. Because yeah, if not P is true out here, that means Q must also be not true. So these two statements are also contrapositives. And so yeah, the original if-then statement and its contrapositive, they are logically equivalent. And sometimes it's easier to prove a contrapositive than it is to prove the original statement. So that's a proof strategy we'll be using sometimes in the proofs in class. Now, there's also a thing called a bijection, the statement P if and only if Q. That means P and Q are equivalent. It means like we have both of these situations combined, and the only way they could both be inside of each other if it's like the same circle. So that's what it means when you have P if and only if Q. Now, to prove P if and only if Q, you have to prove both of the parts of it, both if P then Q and its converse, usually. There are some times where you can write a proof where you have a bunch of if and only if statements you can connect together, but usually you have to do if P then Q and also prove if Q then P. Okay, let's look at example 3. Suppose that n is an integer, show that n is odd if and only if n squared is odd. So what we need to prove is that if n is odd, then n squared is odd, and also if n squared is odd, then n is also odd. So let's do some scratch work to think about this. We can start with some odd numbers for n, like if n is 9, 9 is 2 times 4 plus 1. That's going to make n squared be 81, yeah, which is odd. We can get that by doing 2 times 4 plus 1 squared. That's going to come out to be 4 times 4 plus 4 times 4 plus 1. Yeah, that's 2 times something plus 1. Okay, that works. What about proving the converse? Maybe we can think of a different n squared. Like if we think of an a square of a number that is odd. 25 is 2 times 12 plus 1. I know that n is 5, but how can we go backwards from like the square root of 2 times 12 plus 1 to get 5? I'm not sure how to do that algebra. So, yeah, I can see that going from n squared being odd to n being odd is tough. Okay, we'll keep that in mind, but we did a little scratch. Let's go ahead and try the proof. So to outline it, we need to prove two things: the if p then q and the if q then p. And I'm writing out the want to show that n squared is odd using the definition that n squared is like 2 times c plus 1 for some constant c, some integer c. Okay, so let's do step 4. Actually prove it. And foiling out 2k plus 1 squared gives you 4k squared plus 4k plus 1 squared, which is 2 times 2k squared plus 2k plus 1. Yeah, that is 2 times an integer plus 1. Okay, so we got that part. We still need to do the other direction, though. We need to write, I guess we're going back to step 2 and 3 here. Suppose that n squared is 2c plus 1 for some integer c. We want to show that n is odd too. Now, this is where I kind of got stuck before. I'm not sure what to do with n squared. I'm not sure how to take the square root of it. So, So here's a situation where if you're stuck, you might want to think about the contrapositive. The contrapositive of if n squared is odd, then n is odd. Let's think about it. So the contrapositive of if n squared is odd, then n is odd is if n is not odd, then n squared is not odd. And here again, we can use things you know about numbers, that everything's either odd or even. So in other words, you can say if n is even, then n squared is even. And that sounds easier to prove than what we were just trying to do. Okay, so let's start over with this one. So let's suppose that n is even. We want to show that n squared is even. So let's do it. N squared is 2k squared equals 4 times k squared, which is 2 times 2k squared, which is even because it's written as 2 times an integer. So yeah, we've proven by doing this contrapositive that if n squared is odd, then n is odd, because we said if n is not odd, then n squared is not odd. So we have proven both of these two statements, and we do have an if and only if thing here. So that is kind of a tricky one. let's briefly talk about how to show that something is false. So far, we've been showing that statements are true, but how do you show that something, a statement of the form if P then Q is false? You find a counterexample, which makes P true but Q false. So in this Venn diagram thing here, it's like you need to show that this is not the way the Venn diagram is, that there's really some part of P that comes out of Q. That thing there is a counterexample, if it exists. So let's look at a statement that is not true. The statement that is not true is if a minus 1 is divisible by 8, then a equals n squared for some odd integer n. Okay, so we're going to do some scratch first to just think about it. You might say, okay, 9 minus 1 is divisible by 8. Right, that's 8 times 1. So that number 9 is the a. Oh, and that is equal to 3 squared. Oh, so maybe the theorem is actually true. Have we actually proven that this is always true? If a minus 1 is divisible by 8, then a equals n squared for some odd integer n? Well, we haven't proven that it's always true. Maybe this is just something special about the number 9 and the number 3. Let's try another number that minus 1 is divisible by 8, like 17 minus 1 is equal to 16, which is 8 times 2. So there we go. 17 in this case, is not equal to the square of an odd integer. So a equals 17 makes it true that a minus 1 is divisible by 8, but a is not n squared for any odd integer n. So we've proven that it is false. So in other words, the Venn diagram looks like this guy over here. Okay, so we are done. Cool beans. We got some practice exercises. It's not a lot of it, just to get an idea of like how to get started with a proof when you're stuck. Anyways, good luck with that, and I will see you later.